रिकॉर्ड कैमरे से इससे कुछ नहीं, आप देख भी सकते प्रीव्यू अगर देख रहे हो। नहीं नहीं, घुमाना नहीं है कुछ। ओके ओके। Okay. So, shall we start? Or okay, I'll close the door. Okay, good. So today we are going to start with dual cryptography. So we're going to look at cryptography with certified deletion. Yeah, always. Right. So cryptography with certified deletion. This is a paper by Dakshita Khurana and James Bartusak. I think it's 2022. Okay. Oh yeah, it should probably be Bartusak and Khurana. Yeah, that's true. Yeah. Yeah, it's always so in crypto community it's usually alphabetic. So yeah, I just didn't. Okay, and so that's the actual title of the paper that I'm presenting today. The paper is a little bit. We'll see how far we're able to go. We might need 2 lectures for this, but okay, good. So what I'm going to do is I'm actually going to give you or give you a small construction and to kind of tell you what the setup is, and then I'll formalize. Yeah, so maybe let me write the plan. So what's the plan? So the plan for today is to first give you what is called secret sharing with certified deletion. So it's just a simple construction to motivate the setup. So secret sharing with certified deletion. Then I'll give you sort of an informal introduction. So I'll tell you what the definition is, what we mean by certified deletion in a certain context. I may or may not give you some motivation on how it's used, depending on how much time we have. And I think then I might say a little about how the proof works, proof sketch. Okay. And then after this is done, then I'll go formal, right? Then I'll actually tell you what the yeah. So then this is where the actual class will start, like in terms of defining the security notion and the security proofs. Okay, so that's the plan. Okay, so let's start with point A, secret sharing. So here, what we are looking at is okay. So we're looking at 2 out of 2. So okay, that's the story. So we're looking at 2 out of 2 secret sharing. I actually don't know what the nomenclature strictly means, but this is the setup. Okay, so the setup is that where's the pointer? Okay, the setup is that there is a dealer. So there's a dealer. Let's call her Alice. Okay, and what she wants to do is to share a bit. So she wants to. Okay, you guys can read here, right? It's not okay. So she wants to share a bit. Fee. Okay. Between say Bob and Charlie. And she wants the following guarantees. So she wants them to be such that I'm saying what the constraints are. So she wants to share the bit B with Bob and Charlie in a specific way. Of course, she could just send B to both parties, right? Like that obviously already satisfies this too. So to make it non-trivial, I have to give you some constraints on what I want from this functionality. And the constraints are as follows. So I want it to be such that, number one, the individual views, so individual views of, oh, sorry, Bob and Charlie. Bob and Charlie perfectly hide the bit B. Okay. With the joint view uh, can be used to recover. Okay. So the first point is just the standard notion of secret sharing, right? So you want to give each party some ciphertext derived from the bit B, right? And you want it such that if you only hold, if you look at the local views of the parties to which you've given the ciphertext, they're not able to recover the bit. But if they come together, then they can actually recover the bit. Okay, that's why it's called secret sharing, that you're sharing the secret across two parties, so you cannot get individually. Okay. Bob and Charlie cannot? Yeah, yeah. They cannot individually see B, but if they come together, then they can recover B. Is that okay? No, no. I mean, the requirement is that it perfectly hides. They should not learn anything about B. Yeah. You guys have, cryptography, right? Like you have some background in cryptography or no? No? Oh, okay. So maybe we'll do one or two lectures later on intro to crypto as well. We'll build along for the moment, but at the moment, yeah, you can just think of this as, say for example, you could give to Bob, you could give B plus, say some randomness R. Okay. So to Bob, Charlie could give this object. Uh, and then to Charlie, you know, uh, the share could be R. Okay. And R is randomly sampled, uniformly randomly sampled. So in this construction, you see that Bob doesn't know anything about B because it's XORed with a random bit. Charlie also doesn't know anything individually because it's XORed with a random bit. But if they come together, they can XOR their ciphertext to recover B. Okay, so that's kind of what is meant. Okay, good. So that's the first property we want. So this is called. So this is the secret sharing property, right? Okay, and the second thing we want is the new thing, right? So far I've said nothing about certified deletion. So this is the second property. We want certified deletion. And the certified deletion property requires that, so we're formalizing it in a specific way. So it's going to be asymmetric between Bob and Charlie. The requirement is as follows. So Bob can generate oh shoot, I switched to cursive. Nah, doesn't matter. Generate a certificate for Alice. Okay. To convince her that this is all very wordy. Okay, I'm just going very slow for the moment. We will formalize this. To convince her that B has been information theoretically removed from the joint view. Okay, so that's the key part. Joint view of Bob and okay. So it's the no. That's why I'm saying it's asymmetric. It's just for illustration. We'll do it properly later. So in this very simple example, I'm just saying that I want a scheme which has secret sharing and which allows one party, in particular Bob, in this case, to generate a certificate which would convince Alice that information about B has been removed from the joint view of Bob and Charlie, which means that even if afterwards they come together, they cannot recover B. Information theoretically means, I think I kind of should have done some intro. Information theoretically basically means that you're not assuming that Bob and Charlie are computationally bounded in any way. So even if they have like infinite computational power, they will not be able to recover. Uh, yeah. Okay, so like there's no information about it. It's not a limit on the computational power of the machines. Okay, is that okay? Okay, good. So now what we're going to do is I'm going to give you a very intuitive construction, which I will assert satisfies this definition. We'll not prove this. We'll prove the version which is more general. But the statement would be something like this. Okay. Yeah, this I don't remember. I forgot to look it up. So I think you're probably splitting it into two parties, and if two of them come together, they can recover it. So I'm guessing that must be the total of two, because it could be that like if you have like k parties, then some small enough subset, if they come together, they can recover it. Something like this. Okay. So okay, so what is the scheme? So here's the scheme from some previous work of Bartosek and Purana. And the scheme is as follows. So Alice does the following. So she samples uh, a string of length lambda x, and she samples a theta also of length lambda. Okay. And then this is what she does. So she sends to Bob x where the basis is determined by theta and the value is x. Okay, so I'll explain this if you're not familiar with the notation. Let me just write it. And to Charlie, she sends theta, b prime equals b, XORed with I such that theta I is 0, x above. So this is basically just the BB84 state. Okay, so for example, I'll give you an example of what I mean by this instead of being. Yeah, so formally, okay, let me just say what formally this means. So this is h theta 0, tensor h theta 1, and so on, h theta lambda. Yeah, let me go from 1 to, so it's probably easier. Okay, acting on x1, x2, double dot x lambda. Right. So this state is just this. It's shorthand for the state. Okay. Good. Notation is clear. Okay. Yeah, exactly. So this is basically just a bunch of BB84 states. If you know BB84, right? So it's either, so the states are going to be either 0, 1 or plus minus. Right? So each individual qubit is going to be in one of these states. Okay. She sends the state, right? So she sends h theta x. So she prepares the state. So she's okay. That's an important thing which we look at. So this is a quantum state. Okay. And this is classical. What is sent to Charlie? Okay. And this is something that I mentioned in the first lecture, but I probably should have recalled that the notion of certified deletion, we'll formalize it more clearly, so it'll be clear, but the notion of certified deletion does not really make sense in the classical setting, because whatever information I have, I can always copy it. There's no restriction on copying the information. So there can never be a notion of information theoretically deleting information. Okay, so it necessarily has to be that there is some quantumness somewhere, and in this specific example, Bob is getting a quantum state, which is which can be removed at some point. We'll see what that means. Huh? Yeah, yeah. That's the bit. No, it's the definite. Yeah, yeah. So B is the main thing. So B is the bit that she wants to send, Alice wants to send. And this is the scheme that I'm describing. So yeah, if you can say, suppose that she has the input B, if you like. And then this is the scheme that she uses to send it. Okay, and these are the states. 0, 1. So yeah, so I was just saying that NB, each qubit is in one of these states. Okay. Okay, good. So now yeah, sorry, is it too small? Yeah, it's just I such that wherever theta is 0, you take exactly. Yeah, so I was going to describe what Charlie's state is. So let me do that. So Charlie gets what? She gets the he gets the Charlie's a he, right? So Charlie gets uh theta, which is the basis, right? And then additionally he gets the bit B masked with some string, okay? With a bit. And what is this bit? So this bit is basically looking at all the thetas that were encoded in the computational basis. Okay. So all the thetas here that were encoded in the computational basis, sorry, all the x's that were encoded in the computational basis, because theta is saying which basis it's encoded in. So all the x's that were encoded in the computational basis, you take the XOR of those to get one bit. Okay. And then you XOR that bit with B. Okay. Is that okay? Yeah. Oh, it's just saying each qubit is in this. Yeah. Yeah. So I was just saying each qubit in this, so these are like lambda qubits. So each qubit in these lambda qubits is going to be either 0, 1, right? Because theta, if theta is 0, then it doesn't act on all otherwise. Right? It's just to make sure. And it's good to get familiar with the notation. Okay. So if you have questions about the notation, ask because it will get much more complicated very soon. So you have to make sure you're following. Okay. So far, so good. Okay. So now let's check. Oh, sorry. I still have to tell you how this deletion certificate is produced, right? So the certificate part I haven't told you. But before we do that, let's quickly check that intuitively, at least, it satisfies property 1. Okay, so property 1 is sort of easy to see. So first of all, Bob has no information about B whatsoever. Correct. Yeah. So clearly, Bob, information theoretically, cannot learn B because he didn't get any B. Charlie, on the other hand, does get a B, right? However, he has it XORed with some string which was randomly sampled, right? And he doesn't know anything about the string, right? So Charlie, he only knows theta, right? But theta and x are independently sampled. So there's no correlation between them. And so therefore, Charlie also does not have any information about the bit P. Okay. But each bit is randomly sampled. So it's fine. Yeah, when I say you sample a random string of length lambda, it means that every single bit is uniformly random, right? Yeah. So here, if you XOR two random bits, you get a random bit. That is true. Why we are XORing will become clear later because we want to argue that there's like a notion of certified deletion. So that after you get certified deletion, even if they come together, they could not have recovered. So that's why there's the XOR. Otherwise, it's the same. Like classically, what I was saying, right? Like you send R to Bob, and then to Charlie you send B XOR. So one bit was enough in that case. But we also want certified deletion. So therefore, we are making it a bit more complicated. Okay. Distinguish between what and what. Yeah, so what you want to distinguish between is whether Bob can learn anything about B. So when B is 0, Bob sees a random bit. When B is 1, Bob still sees a random bit. So, sorry. Yeah. Yeah. Yeah, yeah, yeah. Yeah, yeah, yeah. 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 Any more questions? Is it okay? Okay, good. Um, so this is the scheme. And okay, so secret sharing, right? We already saw the intuition for secret sharing. So intuition. So point one. So secret sharing is satisfied, right? So this we already agreed. Secret sharing satisfied because, so Bob sees, so Bob never learns, never sees B. Okay. And Charlie's, okay, for Charlie, B prime is XORed with a random string, XORed with a random bit actually. Random bit, right? So this is fine. But of course, they should be able to recover B prime once they come together, which of course they can, right? Because if they come together, Charlie can, Charlie knows theta, so they can remove the Hadamard by applying H to the theta again, right? Recover X, and once they have X, they can remove the XOR, right? And so Bob and Charlie together can apply H to the theta to Bob's state, learn X, and recover B from B prime. Okay, so this part is okay. So now let's look at the non-trivial part, which is how the deletion certificate is issued. Okay. Yeah. Yeah, of course. Okay, so the first principle in cryptography, yeah, maybe I should have. The first principle in cryptography is that for historical reasons, that you never assume that the protocol is secret. You always assume that the description of the protocol is publicly available. Okay, so we will never consider protocols where the security derives from the fact that the protocol is not known to everyone. So this will always be. Yeah, yeah. So basically, you have to, it's a BB84 state, and so you're going to ask for some measurements on some basis, and then we'll see. Yeah, yeah. That's equivalent to this, right? Like I was saying. So you have some random bit R, and then so if you did not care about the certified deletion, then this is enough. Yeah. So the whole point we're adding the Hadamard is so that we can have some notion of deletion, which is the interesting part. Okay. Okay, good. So like Aryaman is it? Yeah. So like Aryaman was saying that we will have to do some kind of a measurement. And what the deletion certificate is going to be is as follows. Okay. So the deletion certificate. So this is part of the definition of the protocol. Okay. So the deletion certificate is the following. So it is going to be that Bob measures all the qubits on his qubits in the Hadamard basis. To get X prime. Okay. So that's the certificate. Okay. And this is the certificate. Okay, and Alice needs to verify, right? She has to check that the certificate is valid. So Alice's verification procedure is the following. So she's going to check wherever theta I. So wherever theta I was 0, so you take whenever I is such that theta is 0, you want X prime I to be the same as, to be 1, right? Sorry. X prime I to be the same as Xi. Okay. So intuitively, what is happening is that Bob is supposed to measure. So he doesn't know, right, whether he has 0, 1, plus, minus. He doesn't have any idea. So what Alice is asking Bob to do is to measure all the qubits in the Hadamard basis and send it to her, whatever result he got. And then Alice is going to check wherever it was indeed encoded in the Hadamard basis, right? The answer should match whatever she had encoded. So the crucial thing is Bob doesn't know which bits are encoded in Hadamard and which are encoded in computational basis. Because if he tries to deviate, he will get caught in at least one of them. Okay? So it's very difficult for Bob to, so we'll prove this more formally, but the bottom line is that with negligible probability, or let's say with essentially probability 1, Bob would have measured everything in the Hadamard basis if this test is passing. Okay, we'll formalize what that means, but yeah, it'll not quite be that. It'll be close to Hadamard, but it'll be enough for our purposes, and that's kind of the main technical core or technical contribution of the paper. Okay, yeah. Yeah. Cool. Yes. Yeah, because the security, did I erase the security? Oh no, it's here, right? So you want it to be such that, so that is a good point. So just to repeat the question is, if Bob and Charlie came together first, right? Then they could have produced B and a valid deletion certificate. Because if they come together, they have all the information essentially that Alice has. So they can produce whatever, satisfy whatever verification procedure Alice is using. So the key thing is that the deletion process must happen while Bob and Charlie are not communicating. Only then do you get any guarantees. Okay, otherwise there are no guarantees. And this will be a running theme, right? We'll assume that the underlying setup is fine, and while the setup assumptions are true, if you issue a deletion certificate, then you get a stronger guarantee, which is that even if the setup breaks down, which in this case means that Bob and Charlie actually start communicating after Bob has issued a deletion certificate, then they cannot recover. Even then they cannot recover. But that's the whole point. Okay, because of course, if they cannot communicate, then you don't need to delete anything. They cannot see it. It just happens to be the case. Okay, so that's the idea. Good. Okay. Okay, so this was the procedure for deletion. This is the procedure for Alice's verification. And so now continuing with the intuition for how the second step is satisfied, intuition 2. So one can show that, this is an assertion. So you can show that if Bob produces a valid certificate, Bob, yeah, and this is the key part, like without communicating with Alice, with Charlie. Right. Then with probability 1 minus negligible, he measured almost all his qubits in the Hadamard basis. Okay. And once we know this, right? So once you have this fact, then because at least some of the qubits, right, almost all of them essentially were measured using Hadamard, right? So which means that at least one of them with essentially probability 1 was measured in Hadamard. That means you lose all information about X. Okay? So if you measure a qubit X, which is, so basically it's saying like if you measure the plus or minus state in the computational basis, you get 0, 1 with equal probability, right? So what that means is that the XOR over here, you wanted to know what the X was, right? So if even one of the X's is uniformly random, the whole string is uniformly random. So that's what ends up happening, because since you have this guarantee that if the test passes, then essentially Bob was measuring all the qubits, essentially all the qubits in the Hadamard basis, which means that he would have measured even the ones that were encoded in computational basis in the Hadamard basis. I said the argument the other way, sorry. So it's 0 and 1, and he measured in the Hadamard. Let's say he lost all information about whether it was 0 or 1. Exactly. So now, even if they come together, there would be at least one of the X's here that would not be in the that information about which is completely gone because of the this guarantee that you mentioned in the happen. Yeah, we'll formalize these things later. Yeah, for the moment, it's just intuition. Like Nagel and so on, we'll see. It just basically means like for the moment, you can think of inverse exponential in the security parameter. So things that go like e to the minus lambda for the moment. We will formalize it. It basically means that it's smaller than 1 by polygon. So it's okay. It's just a very small function. So as you increase lambda, it rapidly decays. Negligible. Yeah. Yeah, I'm sorry. I kind of assumed. I was told that you guys don't know quantum, but you know crypto, and I think it's the other way. Like if you guys know quantum but not crypto, so I spent like the first 3 lectures doing the exact opposite. It's so dumb, but okay. Okay. So this is fine. This is just the intuition. Okay, the actual proof is a lot more involved. So we'll go through it. But even assuming this works, right? There's more work to be done because what we are going to show is a more general compiler. So we're going to show that you don't have to have this spatial separation sort of setting where Bob and Charlie are not talking to each other. You can do it with a single device. And for that, I am going to switch. I think they came up with it. I'm not sure to be entirely. I'm not entirely sure if it was known before, but I think they came up with this. And then what they do is they start with this, and then they find a way of compiling it into something more general. Okay, so we'll see what the idea is. The idea is actually very, very cute. Yeah, they prove that. Like I just gave you the intuition in the paper. They actually prove it. I'll not prove it in class. I'll prove the more. Yeah, they prove everything. Yeah, they prove everything. It follows from like so there are results in QKD and so on. Yeah, this is the main part. Yeah, of course. The other things are yeah immediate. So, okay. So now what we're going to do is the following. So I'll tell you what the okay. So I will tell you how the construction works for uh, like how the what the definition of the general compiler is, and give you the definition of security for that, and then maybe say a little bit about applications, and then I'll tell you how the give a proof sketch, and then we'll do the actual proof. Okay, so that's the plan. So let's start. So we have this scheme, right? The key thing over here was that Bob was not supposed to be able to see what Charlie has, and conversely, right? So in particular, if Bob is the one issuing the certificate, it suffices that somehow Bob cannot access Charlie's information. Okay. Um, so what we can imagine doing uh, is trying to generalize this construction to a scheme where you have some notion of encryption. Okay. So suppose you have a procedure that allows you to, yeah, okay, you guys don't know crypto, so I'm not sure. Sorry? They can have what? If they come together, of course, you can produce this. That's what Ariman was saying, right? Yeah. The guarantee is only in the case that you produce, when the certificate was produced, they were not allowed to talk to each other. It's a setup. It's a setup. It's just a building block. Yeah. It's true. It's not general. I'm going to show you how to generalize it now. But the construction here was assuming that that there are two parties that cannot talk to each other, and you give them these two shares. And the statement was that individually they do not learn anything about the bit, but if they come together, they can learn it. And if one of them issues, like it should be possible for one of them to issue a certificate saying that, we're not together now. Here's the certificate, and the certificate, if it passes, guarantees that even if they do come together later, they cannot recover the bit. Yeah, I don't know actually if there's something that breaks immediately. I've not thought about the variants, but mhm. When? Yeah, but that defeats the point of. Does it defeat the point? I mean, then if you have this, then you might as well not have sent B, right? You just send it B when you wanted to send theta. It's like, what's the point of sending? Yeah, but okay. So what you're describing is this, right? You're saying somehow that you give. So to Bob, you give x h to the theta, right? And you give him b prime, right? And you're saying at a later point when, so this is, say time t0, and at t1, when uh, Alice wants Bob to learn b, she sends theta, right? But how is it any different from not sending anything at all and then just sending b? You're not. So you're still in that setting that there's Bob and Charlie, or are you in the setting there's only Bob? Okay, so there's only Bob. Okay, then what is this buying? What is the purpose of this? Well, what functionality is this bringing? Who's everybody else? There's only Alice and Bob. Okay. Okay. So there's okay. Let's not build other schemes. It takes a while to analyze them, but we can discuss it a little bit later. But the yeah, yeah. So let me formalize it. It's possible what you're describing actually works, but it's hard to prove because a lot of the constructions are done the way they're done, so you can actually prove them. So it could be that giving access to this xh theta is difficult to work with when you're doing the formal proofs. It's just easier to keep this hidden as well. So there are possible I haven't actually built the scheme myself, so I don't know which are the other things that fail. So there's that. But I can tell you the one that they present in the paper, which is the following. So what they describe is, uh, yeah, okay. So let me actually rewind a bit and tell you what the focus. So here we were looking at 2 out of 2 secret sharing, right? Now we're going to look at encryption with deletion, right? So encryption schemes with certified deletion. So encryption with certified deletion. So this is what we're going to build towards now. Okay, so we're going to look at the following set of algorithms. So a scheme like this will be given by a bunch of algorithms. So there'll be encrypt, there'll be decrypt. Okay, these are all efficient algorithms. There would be a delete, and there would be a verify. Okay. So these are the various things. Okay, but there's also a key generation algorithm. Right? So there's a gen. Okay. So the generation algorithm, we're going to use public key encryption for the moment. So if you're probably familiar with public key, we will introduce things as we need them. So you run gen 1 to the lambda. Oh, that's actually a good point. I forgot to silent my notifications as well. Should do that. Okay. So we run gen to the. We have till 11:30, right? Yeah. Okay. Okay. Good. So you run gen 1 to the lambda. You'll get some public key and some secret key. Okay. You run encrypt on the public key. Sorry, using the public key on some bit B, and it will produce the following. So it would produce a verification key, okay, and a ciphertext, okay. And this ciphertext is going to have the following form. So it will have a quantum part, and it will have a classical part. Okay. Public key. Sorry, the letter you meant. VK is the verification key. I'll describe. I haven't described it yet. But yeah, VK is the verification key. PK is the public key. SK is the secret key. CT is the ciphertext. And the ciphertext is going to be of this form, where the first part is quantum and the second part is classical. So we'll just pass it like this. Then there's delete. So delete, given the ciphertext, is going to produce some message M. Oh, sorry. It's going to produce some V, which is the certificate. And the verification procedure is going to take V, and it's going to take the the verification key, and it will tell you whether you accept or you reject. Okay, so this is the symbol for accepting, and this is the symbol for rejecting. Okay. Okay, good. So since you guys don't actually, not all of you at least have a background in crypto, so let me say a little bit about how you formalize security, right? So first, I need to tell you security for what. Okay, so security for of the encryption scheme. So security of encryption. So at the moment, I'm going to give you a slightly weaker notion of security. For public key, you have to have like a slightly stronger. No, they're equivalent actually. Okay, fine. Sorry, take that back. Uh, so here's the notion of security for the encryption itself. So the way this is formalized, and I might be slightly wrong because I'm doing it from memory, but the way it's formalized is as follows. So you mentioned that there is a challenger. Okay? The challenger does the following. There's a challenger and there's an adversary. Okay. So there's going to be, so I'm going to define the security of the encryption scheme in terms of an interactive procedure between a challenger and an adversary. And I will make so the output of this interaction is what we're going to use to define the security. Okay. So the way this works is that the challenger samples, so gen 1 to the lambda. 1 to the lambda, first of all, I guess you already know this, but in this area of CS, it's very common to write 1 to the lambda, which just means a bunch of ones. Okay, so lambda many ones. That's just standard. Huh? Did I mess up? Yeah, sorry. Thank you. Yes, the secret key. Okay. Yeah, 1 lambda is basically just notation for lambda many ones. Okay, similarly, 0 lambda and so on. It's not 0 to the power lambda or 1 to the power lambda. That would be redundant. Okay, good. So the challenger starts with running gen on some security parameter, lambda. So 1 to the lambda, and gets the public key and the secret key. Okay. Okay. It sends since it's a public key, it sends the public key to the adversary. The adversary sends two messages of its choice, x0, x1. So the adversary can pick any two messages it wants. Okay. So for the moment, let's assume they're bits for simplicity. So, or actually bits would probably be wrong. So let's just say that they're messages. Let me write it. Do we have M? We don't have M, right? Okay, good. So yeah, so it picks messages M0, M1, okay, of size poly and lambda. So these are, they are strings of length poly lambda. Okay, so these are standard crypto things which I'll use here. So there's poly lambda. So poly lambda is some polynomial of lambda. So it's slight abuse of notation. So I'm not specifying exactly which poly, but some polynomial or bounded by a polynomial of lambda. There'll also be this negligible and things that we'll describe and look at here, and so on. Those are things I'm just writing because you can look it up later. It's not crucial at the moment, but nonetheless, it's good to know them. Okay, so the adversary has these two messages, and the adversary sends both messages, M0, M1. Okay, to the challenger. The challenger is going to do the following. The challenger is going to pick. Have we used B already? Okay. So it was encrypting B, right? Do I want to use the same thing? Okay, so let's say B tilde. Okay, so it picks B tilde, which is either 0 or 1. And then it encrypts using the public key one of these messages at random, right? Because it sampled B uniformly. So it encrypts one of these messages, gets a ciphertext CT, okay? And then sends the ciphertext CT to the adversary. And the adversary has to make a guess, say B guess, let's say B tilde guess. Okay. And the challenger accepts if B guess matches B tilde. Okay. Okay, so we'll say that this scheme is secure. So, okay, so the security requirement is that the probability that the challenger accepts in this game, right? So challenger accepts given this indistinguishability game. Yes, let's call this game int. So the challenger gets lambda. Yeah, the adversary can also get lambda. So the challenger accepts int is supposed to be at most half plus a negligible function of lambda. Okay. Yeah, so negligible for the moment is very small. Like you cannot multiply it with a polynomial and make it non-zero. Well, not non-zero, but not negligible. Okay, so this is the notion of security. So, okay, so I've not even talked about certified deletion. I'm just saying that an encryption scheme is secure if it satisfies this property. Is it okay? Are there any questions on that? Oh, indistinguishability. Okay. So I didn't understand. So after decryption, can we get back? Oh yeah, it should be B, right? I don't know why I wrote V. Yeah. What is V? Did I mess up? Oh. I think, yeah, I think I didn't write decrypt. Yeah, thank you. I think I messed up. Sorry. So if you decrypt, you should get B. In fact, it should be deterministic, but yeah, let's just say it get B. And this should be delete. Sorry about it. Thank you. Thank you for catching spotting that. Yeah, because when you decrypt from the ciphertext, you should recover what you encrypted, right? That's just correctness. So let's write that as well. So correctness of encryption. So this says decrypt using the secret key CT, secret key of B. Yeah, maybe let's call it B prime. I kind of implicitly assumed you get B. Okay, normally it will give you some B prime, and the security would be that B prime matches B. So, so yeah, let's just keep it for simplicity to be the same as B. But the condition is that if you get decrypt plus B prime, you should get B if encrypt PK or B is how you generated C2. Okay, so if you generated the ciphertext, you should get the same. So if you encrypted B to get the ciphertext, the decryption should recover the same message. So that's correctness. Security is that you have this experiment and no adversary that's, so if it's quantum, you'll say quantum polytime. If it's classical, you'll say classical polytime. So as long as it's computationally bounded, you want this condition to hold. It's also called semantic security, but in this case, it matches CPA. We'll look at those things later. Okay, so this is the notion of security we need. And deletion certificate. Okay, so now we can describe the what we mean by the deletion. Okay, so deletion basically here means the following. So okay, so the intuitive definition of certified deletion. Certified deletion. Okay, intuitively, what this means is that, so suppose an adversary is QPT when the deletion certificate V was produced. Okay. Then if Aleph uh, verifies V successfully, successfully, then it implies that V is information theoretically deleted. Theoretically removed from A's view. Okay, so that is the requirement. So that's the intuition. So what is the intuition saying? That once you successfully produced a deletion certificate, and assuming you were computationally bounded, you were QPT when you produced the deletion certificate. Huh? Oh, is my handwriting not legible? Oh, shoot. Okay. No, I'll write it properly. Yeah, maybe I shouldn't use cursor. I forget. Okay, so suppose A is QPT when the deletion certificate V was generated. Okay. Is it legible now? Sorry, you should have told me earlier. I get excited and I go, oh, so the handwriting was okay, but you couldn't see because I was standing. Yeah. Okay, got it. Yeah, it would have. Okay. Got it. Thank you. Okay, good. But now it should be clear, right? Even if I don't read out the thing. Okay. Interesting. It's a streaming problem. Okay, good. So suppose A is QPT when the deletion certificate V was generated. Okay. Then what we want is the following. So we want that if verification of V is successful, then V is information theoretically removed. The information theoretically removed. Theoretically removed from the adversary's view. Huh? Oh my God. Oh, shoot. Okay, I'm so sorry. So QPT is just saying that the, polytime, have you done any complexity theory at all? Okay. So polytime is that the number of gates is polynomial, right? So in this case, you just said the number of quantum gates are polynomial. That's all. Yeah. Yeah. So intuitively so it's very analogous to what we had here, right? So here we were saying that what is the setup assumption? The setup assumption was that Bob and Charlie are not talking to each other, right? And then Bob is able to generate. So if Bob generates the deletion certificate while the setup assumption was true, then even if the setup assumption breaks down, you cannot recover the whatever B was said, secret shared. In the case of encryption, we're assuming that the guarantee of the encryption is when this. So let's say okay, so when maybe I should write it when A is cryptography. So the security guarantee only appears when you're playing against adversaries that are polytime, right? That are quantum polytime. So as long as they are quantum polytime, you have security. And the certified deletion is saying that as long as the setup assumption, which is that they're polytime, right? So if this setup assumption is true, when the deletion certificate was generated, yeah, then afterwards, if they become unbounded, even then they cannot recover the secret. That's the point. During the production of the certificate, yes. And obviously, because just from the security of the encryption scheme, already the adversary cannot learn B, right? Because so there was nothing to do. So it only becomes interesting if you ask them to produce some deletion certificate and then later allow them to be unbounded. And even then they cannot. Okay, so there are different flavors of how you strengthen this. This is probably the most general notion. There are weaker ways of also doing it. Like you can say, what if the public key, the secret key gets leaked later? So it's not that they become unbounded, but just the secret key gets leaked. Things like this. So there are weaker ways of formalizing it. But here we are saying that as long as the certificate was produced when the setup assumption was true, if the certificate verifies, then even if they become arbitrarily powerful, they will not be able to learn the encryption. Okay, good. So let's formalize this. So these are just words. We need to formalize what we mean. So let's write down the definition. All of this is semi-formal. Okay, I'll do the actual proofs in a little bit. But an almost formal definition is the following. So suppose, so we define the security game. Yeah, because so you remember there are different things that you can do certified deletion with. So that was secret sharing with certified deletion. This is encryption with certified deletion. Yeah. But the nice thing with the secret sharing with certified deletion is that we'll be able to use those ideas and construct a scheme for encryption with certified deletion. Okay. And we'll be able to do it quite generally using the ideas. Okay. Any more questions before I write on? Okay. So the security definition now is the following. Security for certified deletion. Okay, so the security condition is as follows. So you're going to run, so in cryptography, if you're not familiar with it, maybe it's worth mentioning that almost all security definitions that we are going to encounter, except for, like maybe when we do NPCs, they're going to involve a challenger and an adversary. Okay. So the way it's formalized is that there's a challenger that, as before, samples the keys. So onto the lambda. Shoot, she started using K for some reason. Doesn't matter. Let's use lambda. If I start using K instead of lambda, tell me, because I'm reading from the notes and the notation is a bit different. Okay, so PK and SK, they sample the key. They encrypt it. They encrypt the bit B, right? So the challenger gets B as an input. They encrypt the bit B to get the ciphertext CT. Okay. And then they send the public key and the ciphertext to the challenger, to the adversary. So here's the adversary. Okay, and the adversary sends is supposed to send a deletion certificate. Okay, we do not know because the adversary is untrusted. So they're supposed to send some certificate V. Okay, and they will send, say, A prime. Okay, so yeah, maybe this is a good moment to pause for a second and set up some conventions. I am going to use a slightly well, the notation is not going to be symmetric between classical and quantum. So for classical messages, I will just write the message itself whenever it's being sent. For quantum messages, I will write the register name that is being sent. And the state will be implicit. Okay. So for example, it could be that V is correlated with the state on A prime. Okay. but I'm not writing the state explicitly. Okay, so for example, it could be that there is some distribution over V, so there is some probability of getting V, and so the state would be like this, right? So this is the classical bit, and then there could be some possible entanglement, or probably something even more general. So it could be that the state is of this form. This A prime, and this is the register V. Okay. So even to express things of this form, I will just say that you got the outcome V, okay, and then you got psi V somehow, which is potentially correlated. Notation's fine, right? I don't see anyone nodding at all, so I'm not sure if it's completely trivial or if it's not clear at all. Yeah. So you'll see little letters like, you'll see classical things will be, X, B, A, B, these kinds of things. And I'll typically use capital letters for registers. Okay. So this is just saying that you send the string B, because remember V is, I didn't say that, shoot. Okay, so V is classical here. It's good, okay? So V is classical, these are all classical. So I'll underline the things that are classical, okay? So V is classical, CT is classical, this is classical, okay? And these things are also classical. Okay, so underlined are classical. And basically bit strings. Okay. So the adversary sends some V, and now what you do is it sends V and it sends the residual state, okay? So you're just assuming that it's just a way to formalize it. So this denotes that the entire system that the adversary has been sent. So the adversary has nothing left. Okay, this is just an assumption for defining the security. It's not that in practice you require them to send everything they have. This is not needed. Okay. Okay. So now if V verifies successfully, you output register A prime. Yes. So verify successfully is this verify using the verification key. Oh yeah, you also got a verification key, right? When you encrypted. Yeah. So verify using the verification key, the ciphertext. Oh, sorry, the deletion certificate. Okay, so verifies correctly means that you got accept, and if so let's say this was the result. So if we verify successfully, that is res is accept, and else if res is reject, the output bot. Okay, so that's the success game. Or residual registers. Okay. Okay, and the condition is the following. So the condition is that so let's call this experiment B, 1 to the lambda. So the requirement is that experiment 0, 1 to the lambda minus experiment. Yeah, less is the trace distance. Okay. And this is the output. So experiment. Okay, TD is trace distance. So approximately means that they're negligibly close. X is the experiment. X is this experiment. So you run this interaction with whichever adversary you want, and you get some output. So So for all adversaries. Sorry, just a second. Say it again, sorry. V comma A prime. Where's V comma A prime? Uh, yeah, sorry. He sends the classical state and whatever residual registers he had. So he sends everything basically. Yeah, I mean, you interpret it like, if somebody sends you some state, you interpret the first part as classical. So it's fixed. You know that it's the first lambda many qubits are supposed to be classical bits, and everything else you treat as quantum. Yeah, it's the value of the classical register. Yeah. 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 Exactly. It's just that writing the full classical quantum state makes things very, very complicated. So here, all that we're doing is you're saying, ideally, I would like to say, send V and some states high, but that's not true because, they could be correlated in some weird way. Yeah. So yeah, if you wanted to write it strictly, you could say, just sending the register V and A prime. That's all. Okay, and V just happens to be in the computational basis, like you said. There's nothing deep happening. I'm writing these kinds of things because at some point there would be entangled states with A prime could potentially be entangled with things over here, right? So I don't want to kind of mess things up. So I'm just writing registers when it's quantum states, and when it's a classical value, then you can just write the class. It's what I independent. No, that's independent CC is like you have access to the decryption oracle and all that. Like there's no. Wait, why did you think? I'm sorry, I'm kind of missing. Why did you think it was in CC? Okay, yeah. Yeah, no, that's a different notion. So, you have CPAs when you have access to the encryption oracle, CCAs when you have access to the decryption oracle. And here, yeah, we're doing something very different because what we are saying is that, uh, yeah, okay, maybe before I go on, is that at least the notation clear? Is Oh, yeah, this is just the output of this experiment. So you run this interaction, and whatever output you get is given by exp. So x0 would mean that you run this, you take b to be 0, you run this experiment, and you look at the output. X1 would be run it with the initialized to 1, you look at the output, and you'll get, this will be a quantum state, right, in general, because you're sending one of the registers out. And then the claim is that the quantum state is going to be statistically indistinguishable because it's close in trace distance. Is that okay? Yeah. Yeah, no, that's what I'm saying. You're basically just sending a classical string. You can write the classical string in as a mixed state, right? It's not a like how do you describe a there's nothing very deep happening, right? Like so if you ooh, I can access the side of the board now. Okay. So, it's just saying something very simple, right? It's saying that, if with probability k, you got little k, right? So I'm just writing it as sending little k. It's a random variable, but if you were to write it in the quantum notation, you would say that, I'm sending this state, right? So then I would say I'm sending the register k. So I'm just mixing these notations. Classically, it's much easier to do this, right? Like when you're sending little k, which is drawn from this distribution, you just say, okay, I sent the message k. And quantumly, you don't do that because it's more complicated. So you write the name of the register. So instead of writing names for the classical registers, I'm just writing the random variables directly. That's it. Yeah, yeah. There's nothing deep. It's OTD, trace distance. Yeah, yeah. So I should also clarify this. Yeah, maybe I can do it on the newly found land. So TD rho sigma is basically that rho minus, oh yeah, the trace distance between rho and sigma is at most negligible. Okay. Yeah, negligible because these are functions of lambda, so it's negligible in lambda. They're functions of lambda because everything was parameterized by the security parameter here. Right? Okay, good. Okay, so before, because we have about 7 minutes now, I think. Yeah. So what I'll do is I will not. Yeah. Let me just quickly try to emphasize why this is the right notion. Okay, because so far we just looked at what the notion is. Why does this match the intuition? So it matches the intuition because what are we saying? We're saying the adversary is QPT, right? So the adversary is QPT. It produced V, okay, and it held some A prime, okay, which was the residual part. And what we are saying is that whatever A prime the adversary was holding, conditioned on V being successfully verified, yeah, this A prime is essentially independent of little b. It is. That's the key thing to understand because the register A prime, the adversary. So think about it this way. So the adversary until this point is QPT. It produces V, and then it's holding A prime, and it can do whatever it wants with A prime afterwards. And the fact that it can do whatever it wants with A prime later is captured by the fact that the A prime, yeah, exactly. So the A prime, whether it was produced while interacting with B equal to 0 or B equal to 1, is statistically essentially the same. Essentially because it's negligibly so. Okay. So it's a very beautiful formalization of the entire notion that checks out. It's just a game, yeah. This is just it's formalization as a game. You can formalize it in a different way. But the key part here is that whatever state A prime is left with the adversary, it cannot possibly be dependent on little b. That's the key part. Because when you use it in practice, right? In practice, if you have this guarantee, right? If you have some construction that can give you this guarantee, then in practice you just need little v from the adversary, and you just have to check the little v, and then you guarantee that whatever else it's holding is independent of little v. So this is a security requirement. We'll prove that this can be satisfied, and if it can be satisfied, I was just trying to emphasize that it suffices to actually achieve this intuition that we had to know. Yeah. Why do we constrain ourselves to? Oh, because we are looking at encryption schemes, right? Like this is like standard crypto. You can just build crypto with other assumptions. No, because then you can just break the encryption, right? From CT, he can already recover B. From CT, the adversary can already recover B, right? Because you're assuming that at least the security of the encryption is true, right? Otherwise, the adversary already at this point, if you have CT, right? Information theoretically, CT contains information about B because it was produced. Yeah, but potentially, like for example, if you just have classical encryption, I'm not even saying you're encrypting quantum messages, right? I want this scheme to work in general. So suppose it's just a classical encryption. So what I want is a very general scheme that works in all circumstances. Because then you're kind of already assuming that it has some flavor of deletion. Like you can't do that. All good? Yes. Yeah. It's prime. It's either A prime or perp, but whatever. Yeah. Or it's some density matrix, and you're saying that these two density matrices are identically distributed. Okay. So in the last 2 or 3 minutes, any question? Is it okay? Questions or is it just good? Okay. Yeah, you can formalize it in whichever way because these are quantum operations. So you can say it outputs like some quantum register called out, and then out becomes A prime and out becomes whatever is initialized to all zeros or ones or whatever, or a special symbol represent. Okay, good. All good? Makes sense? Okay. So we have about 3 minutes. So what I'll do now is we'll look at how the how I didn't even give you a construction because the next time I'll give you informally the construction. I will informally show you how this definition is satisfied. And then hopefully we can start with the actual formal proof. Okay. So I will use that part again to quickly say a few things about applications of the certificate. So if you can achieve this notion of security, there are a bunch of very nice things you can do. Um, oh, so it's security for certified deletion because maybe do you want to answer that? Why is this the right notion for certified deletion? Do you want to answer Uttam's question? Because I think you had the same question a second ago. So yeah, why does it capture the intuition? No, you said CT, right? CT depends on B. Yeah. So what you should think of it is as follows. Like, so suppose the adversary until this point was QPT, and then after issuing the deletion certificate, it becomes unbounded. Okay. So if you did not have deletion at all, then obviously when you become unbounded from CT, you could have recovered B. Yeah, A prime doesn't even depend on B. Yeah. He had the encryption and then he produced a deletion certificate. And now the claim is that the residual state he has, which is A prime, that is statistically independent of B. So whether A prime was generated when B equal to 0 was given or A prime was generated when B equals 1 was given, the state is statistically indistinguishable. So the adversary, even if it gets arbitrarily powerful, cannot use A prime to recover B. Yes. What do you mean doesn't have? Information theoretically he has it. He cannot access it because he's QPT in this phase. But later he will become unbounded and he will be able to access it. So you need to perform some procedure. Yeah, then he could recover B, potentially. Yeah, like for example, if you do public key encryption, you can just guess the secret key one by one. Right? You can check all of them. You'll get the message. And also, maybe I should clarify that. And I should also clarify that A prime can depend on the ciphertext. For example, imagine that the first bit of the ciphertext is a random bit which is completely uncorrelated to the message. Like I just, put it for no reason. So then obviously I can copy that in A prime. So the key thing is that it has to be independent of little b. Okay. So I guess we are a little bit out of time. So I'll do the applications and so on next time. But okay, good. Please do fill out the feedback. Huh? I think it's 11:30. We can take it after the classes, no problem. Please do fill out the feedback if you haven't already. And yeah, let me stop the recording.